Hello everyone, my name is Hassani from Max Planck Institute for Iron Research. Today my presentation has two parts. In the first part, I will give an introduction to Pyrion workflow environment, and in the second part, I will show you how in practice one can use Pyrion to create and manage their workflows. I represent a large group of my colleagues from computational material design department in MPIE who, beside their research, are actively contributing in development of Pyrion. The research in the department is mostly focused on atomistic simulation theory. That's why Pyrion has a rich component in atomistic simulation, and but Pyrion is not confined to atomistic simulation, as our department has active collaboration with other departments in Max Planck Institute and multiple research centers and institutes around the world. Here you can see a list of number of our collaborators. Before moving to Pyrion workflow, let's talk about workflow definition. As Tillman already mentioned, one can define a workflow as a chain of well-documented process steps to create or handle data for a specific problem in order to deliver a particular set of outputs. Now the question is how Pyrion can support such workflows and what one can expect from Pyrion. I will try to answer this via a couple of examples. The first example is analysis of an SEM image, where the workflow performs an image segmentation and at the end provide a statistics of grains. The initial expectation from the workflow is to pre-process the image, perform the segmentation of the image, and then producing a statistic of the grain, and the goal is to get publication-ready figures out of the workflow. We should be able to change the initial image and repeat the same workflow with another image. We should also be able to document the workflow and also have the possibility to change the details of the workflow as we run the analysis and or simulation. Here you can see the web front end of Pyrion, where in the left panel you can see that I have a Jupyter notebook open, which includes some code snippets for different steps of the workflow. And in the two other panels, we have the results of the workflow as nearly ready images for publications. As you can see in the notebook, I have each of the steps of the workflow documented beside the code snippets. So far, the initial expectation from the Pyrion workflow is met. But Pyrion has more to offer for a workflow environment. In the second example, let's look at a more complex simulation workflow in which we measure the melting temperature for a given system from atomistic simulations. To represent a simplified picture of the workflow, the structure of a solid which has been brought to a minimized energy is put in contact with a liquid sample of the same composition, and then by iterative adjustment of the temperature and analysis of the speed of the interface between these two phases, the melting temperature for a given composition is determined. Pyrion has a modular structure, and its components are like building blocks put together to create a workflow. First, I have to mention, do not get afraid of the code snippets brought here, as in the second part of my presentation, you can learn more about how they are defined and documented. After importing the needed modules, the first thing that should be done in all the Pyrion workflow is to create a project object. Projects for Pyrion is like a frame for other building blocks to come and be put on this frame. So after the creation of this project, the project gives us some functionalities. One of the functionalities is to create atomistic structure and also visualizing this structure. In the third step, we create a job, a simulation job, which is a molecular dynamic simulation jobs. This is defined as a part of this project. And then then we give the structure to this job, and then define the needed potential according to the composition of the structure. And then we define temperature, pressure, and the number of steps, and simply job.run, perform the simulations, and we can have look at the initial input parameters, and also we can, in the same notebook, analyze the result of the simulation. Here you can see the pair correlation function for the solid state phase that I talked about. At the end, we are interested in a series of simulations to calculate the melting temperature. One can include all the steps of the workflow in a notebook, and then submit the whole notebook to a HPC cluster. So one can simply give the path to the notebook, define the queue that you in the HPC cluster that you want to submit the job, the runtime, and the number, of course, and simply job run. Here you can see the result of the workflow, where the melting temperature is given as a function of the number of iterations. So now that you get a little familiar with the Pyrion workflow, let's talk about design principle which makes Pyrion a suitable IDE for material science. The first one is the ease of use by having a common platform for combining various simulation analysis tools. The second one is interoperability. A common terminology makes it possible to change the one tool with another and perform similar workflow with different tools. Shareability. As I will show you in the second part, you can share your project alongside its results with others at its latest state. Moreover, you can provide a MyBinder link to your workflow so people can test and reproduce your results. Extendability. As Pyrion has an object-oriented structure, one can simply inherit and extend the Pyrion classes for new functionality as it might be required for a new workflow that you are interested in. As I showed in the previous example, Pyrion can easily submit your workflow to a HPC cluster and scale it up easily with numerous cores. The reproducibility of the workflow can be ensured via the Conda environment and Pyrion Docker images. Pyrion has, as I mentioned, Pyrion has a modular structure. This was already explained in Tillman's talk, so I briefly mention it here as well. All modules have their own Conda packages, so that they can be easily that you are not obliged to install all the modules, so you can separately install one or multiple of them as it suits your workflow. A Pyron base includes the general workflow management classes, and all the other modules are built on top of Pyron base. Pyron Atomistic performs atomistic simulation. Pyron Continuum manages continuum simulation, and also Pyron Experimental offers analysis of experimental results. Each module includes and supports simulations packages and analysis packages relevant to their to the purpose of the modules. For example, Pyron Atomistic supports LAMP simulation, VASP simulation, and some other DFT codes. Pyron Continuum supports Damask simulations and Phoenix FEM simulations. Pyron Experimental includes job classes for different image analysis tools. All these Pyron classes, alongside with their dependencies, are containerized via Pyron Docker images, which are available publicly on Docker Hub. As I previously mentioned, Pyron is extendable, and its source code is accessible via GitHub. Pyron GitHub organization includes multiple repositories according to the modules. We have Pyron base, Pyron Atomistic, Pyron Continuum, and Pyron Experimental repository. More importantly, here is for me to mention Pyron Contrib, the repository which is intended for users' contribution, which has its own also Conda package and can be installed alongside other Pyron repository and be used in production. When you want to extend Pyron and you want to contribute to Pyron, you can simply use this repository for your contribution. We have a code of conduct within each repository, which includes guidelines for contributions to the source code. And more importantly, we have an active team of Pyron developers who can support you with your questions and issues. Let's go to Pyron GitHub. github.com/Pyron. It will lead you to Pyron organization and all the repositories that you might be interested in. Here is Pyron Contrib, and you can see that there are active contributors to this repository. You can you can fork this repository, you can make changes and create a pull request, and then your contribution can be merged to Pyron Contrib and can be used in production via Pyron Contrib Conda package. Let's go back to the presentation. One of the possible contributions to Pyron is by integrating your simulation or analysis tools into Pyron. It is according to the level B of the PMD workflows, which was discussed by Tillman. If your simulation tool or analysis tool is in Python, it's a bit easier. It is recommended to make it available as Conda package via Conda Force channel. And then in the next step, you need to create a job class for the package, inheriting from generic job classes in Pyron. then making the job method compatible with Pyrion terminology, like input, output, data, list, etc. If the package that you want to integrate to Pyrion is not built in Python, the path is similar with an additional layer on top. You need to first create a Conda package via Conda Forge channel. Then you need to create a Python wrapper. This is the extra step in comparison with the previous case. You need to use such tools such as PyBinder, Cython, or F2Py to create such a Python wrapper. This will facilitate the data flow between your non-Python tool and the Python packages. Then you, similar to the previous case, you need to create a job class for the package, and then inherit by inheriting from generic job classes in Pyrion. Now we can see the documentation, Pyrion documentation, and how you can find it, and what learning materials are available for Pyrion. These are all available in Pyrion website, pyiron.org. You can go to pyiron.org and move to documentation. It brings you to the documentation parts. It includes documentation for different functionalities of Pyrion. Moreover, it includes tutorials with different workflow examples. Moreover, we have virtual courses with videos, and you can browse in these available videos also from Pyrion website. We have active core developer team, which can be communicated via GitHub issues and Stack Overflows. We have also PMD communication channels like PMD GitLab and MaterialDigital GitHub, which I will mention it in the next slide. Pyrion also provide a template for your workflows. In the MaterialDigital GitHub, you can access this Pyrion workflow template and simply fork it and use it for your workflows. It must include a Pyrion notebook and a Conda environment files. Then it takes care of continuous integration tests, ensuring the workflows is compatible with the provided environment, versioning of the workflow, and configuring the GitHub page for the workflow are done automatically underneath in the template. And it also has a template for the required metadata for accepting the workflow in the workflow store that was mentioned. So in summary, Pyrion is an integrated development environment for digitalizing material science workflows. It includes various features like integration of simulation codes like LAMPS, VAST, DAMAS, atomic recs, etc. It has feedback loops to construct dynamic simulation lifecycle, a hierarchical data management, integrated visualization tools, interactive simulation protocols, and object-oriented job management. So by this, I would like to thank you for your attention for the first part of my talk, and we will see you in the next video for the second part of this presentation.